Good morning, Stats fans. How we doing on this fine, sunny Wednesday morning? Yes, it is Wednesday morning. I know when we get out of our routine, it's sort of tough to figure out what day it is sometimes. It is Wednesday morning. It's sunny out there. Don't let the sunshine fool you, though, because it's a little chilly still. It's a little chilly. But it's sun's warms out there, which is nice. It's nice to see the sunshine here. Hope all's going well with your family. I've received no questions, so hopefully we're keeping up with the material, and we'll work on evaluations towards the end of the week here. We'll get through the rest of the confidence interval. Today we're going to start talking a little about confidence interval when the sample size is less than 30. Okay, by law of large numbers, we want to try to get our sample size bigger than the value of 30. Okay, we want to get as large as possible as a sample size. But sometimes that's not feasible. Suppose I was just doing a study of our stat students, which is 12 kids, and I want to predict out an entire population. Okay, I only have a sample of 12 that I can go with. How can I predict out a population and try to be as accurate as possible? Because I want to, once again, with these confidence intervals, be able to predict out. I've put notes for you to follow along. So you can follow along the notes. I also put a different chart on there. It's called a t-table and a chi-squared, which we'll use later in the week, so I put them both on there. It is a t-distribution table that you will be utilizing. That will be the thing that you will utilize the most for the rest of the year and the rest of the semester in this class. Okay, what happens when the sample size is less than 30? We still want to approximate these populations means with some sort of confidence. So what we use now is we use what is called a t-distribution table. Okay, the t-distribution table is utilized when the sample size is less than 30. When the sample size is greater than 30, I'm okay with using the z-table. But when we're less than 30, we have to revert back to a t-table. But you'll see with our confidence levels and our confidence interval, it's going to be the same. It's just how we find that we had that z for the confidence interval. How do we determine that value now? And we use the idea of a t-value. We maintain characteristics of our z-distribution. Our z-distribution characteristics, we'll still maintain them. Okay, it's still the same idea, but we now deal with a family of curves. Okay, we have still a bell-shaped curve. It's still symmetric about the mean, and if I'm going too fast, once again, just hit your pause button. I'm just trying to reduce the length of time on a YouTube video. Okay, so we're still bell-shaped curve. We're still symmetric about the mean. Okay, still the same. Nothing different there. The mean, median, mode are 0, located at the center of the distribution. That's still the same. The hump, Sally and the camel's hump. We still have our mean, median, mode there. And the curve still never touches the x-axis. These characteristics are still going to be the same. And these will be some of the questions, fill-in questions that you'll have at the beginning of your quiz in regards to characteristics. But what are characteristics that are unique to the t-distribution is what you're going to have to know. The variance is greater than 1. With a z value, we had the variance and the standard deviation equal to the 1. With a t-distribution, the variance is going to be greater than the value of 1 now. The distribution is a family of bell-shaped curves. It's a family of bell-shaped curves based on the degree of freedom, which is based on the sample size. And once again, I will not feel offended if you hit your pause button and continue to write that down. Okay, we have a family of curves that are bell-shaped curves based on the degree of freedom, which is based on the sample size. And as the sample size increases, the t-distribution approaches the standard normal distribution, which is a z-curve. which is a z-curve. So as our sample size gets bigger and bigger, we get closer and closer to a normal distribution. So what this looks like here this is our normal z-curve. This is your normal distribution. This is what we've been dealing with throughout. Okay, we've been drawing these bell-shaped curves. Now what happens with a t-distribution, we get a family of curves. As the sample size gets smaller, we can sort of take a look at this and sort of like squash the sides in from both sides. We sort of take it and squash it in, which starts popping this thing up in the air a little bit more. So what happens is we start getting bell-shaped curves that look like this. So as sample size decreases, the hump on Sally the camel's back starts to get a little bit taller. So as sample size decreases, this starts to get a little bit higher. We don't have to draw it any higher. We can still do our normal bell-shaped curve. Okay, you can still do your normal bell-shaped curve, and we will just adapt off of that. But this is what happens as our sample size decreases. As it continues to increase, we go back to what it's going to look like as a normal bell-shaped curve. So, this is the theory behind what a t-distribution does. The sample size, once again, you'll be asked to give me a characteristic that's unique to a t-distribution. Because we did characteristics of z-distribution in the last quiz, then I'm going to ask you on this quiz, what are some characteristics unique to the t-distribution? So you have to give me one of these characteristics. Now becomes probably the most difficult mathematical concept, because this is based on what is called a degree of freedom. How do we calculate this degree of freedom? This is going to be tough. You may want to pull your calculator out. How do we determine this degree of freedom? Because we have to utilize this degree of freedom. Well, what we do with this, how we calculate this, we take our sample size, n minus 1. So if n is equal to 20, that is our sample size. The degree of freedom is 20 minus 1, which is 19. Whew. Man, that's higher level mathematics right there. That's tough. So we find our degree of freedom. And this bell-shaped curve is based on that degree of freedom. Hopefully you printed out your t-distribution table. Okay? If you have not printed out your t-distribution table yet, go ahead, push pause, and print out your t-distribution. I'm sorry I can't do anything else than just give it to you in that form, and you're going to have to print it out. If you don't have a printer, you're just going to have to maybe split screen this and be able to find it on the split screen at that point. Okay, now that you're back from doing that, for a t-distribution, how do we calculate confidence intervals? Once again, this is a confidence intervals. These are confidence intervals. How do we find these boundary values for a t-distribution? Well, you'll be happy to know it really does not change. But the only change that we have is, these are x bars, we have our t for the confidence interval rather than the z for the confidence interval. So it looks exactly the same of what we just did. The only thing that's different is I'm taking out the t and replace it with a z. I'm sorry, taking out the z and replace it with a t. That's all we've done. That is all we've done. Now hopefully you have your t-distribution table printed out. If not, you're just going to have to split screen this and try to do a split screen, not minimize, but shrink it down so you see the video and also have the t-distribution table sitting there on the other half of the screen so you can look at both of them. If we look at a t-distribution, okay, the nice thing about this table is if we look along the left-hand side gives us our degree of freedom. Along the top of this gives us our confidence interval. So if I have a confidence interval of 90%, I could go to the confidence interval of 90%. And I will have to take and go down the column to my t-value that I need for my value here. The nice thing about this table is if I look at the 99% confidence interval over here, and suppose my sample size starts to get more than 30, which I have a degree of freedom of more than 30 then. Well, if I go to the bottom of this table, what does it say there? Well, it says that's my z-value. So if I go to my z-value, I got 2.576, which we use 2.58, that's fine. Or I could use this value right here. If you look at the bottom of this t-table, they have values that are 2.45. In the textbook, they have values that are used for the z-values. So I don't have to look or memorize those three values I had for the z-table. Don't have to memorize them because I could just pull them off of here now, and it gives me, here's my confidence interval, and here's my z-value. Or if my sample size is less than 30, okay, I can look in here to find my t-value. We made things a lot easier, didn't we? Recent study of 25 students showed that to spend an average of $18.53 for gasoline per week. Standard deviation of the sample size is that should be $3. So I'm going to put a decimal point in there, so that should be $3. I want to find the 90% confidence interval for the true mean. So we have a sample size of 25. We have their mean is $18.53. We have their standard deviation is $3. And I want to find a 90% confidence interval for our population mean. So I'm trying to use my sample to guesstimate my population mean. And that's what confidence intervals do. I'm going to get two boundary values, and I'm going to be 90% confident that my population mean is going to be between these two values. My degree of freedom. How do we calculate our degree of freedom? Well, we take our sample size minus 1. So we have 25 minus 1, which is 24. So to calculate my confidence interval for my population mean, we have our x bar plus or minus my t for the confidence interval times the standard deviation divided by square root of n. Well, we have our x bar, which is $18.53. I need to add or subtract now my t value for my confidence interval. Now we go to my table. My degree of freedom is 24. So along my left-hand side, I'm going down to 24. And you could do this either way. I have a 90% confidence interval, so I can go over my 90%, and I can scrape this down to a value of 24. And if I go down to a degree of freedom of 24, I should get 1.711. So we have plus or minus 1.711 times my standard deviation, which is 3, divided by my square root of 25. Now, this is not the square root of the degree of freedom, this is the square root of my sample size. So I need to make sure I use my sample size here. Now it becomes a clickety-clack calculator exercise. I have 18.53 minus 1.71 times 3 divided by square root of 25, and 18.53 plus 1.711, standard deviation, square root of 25. So I can clickety-clack that through the calculator. Go ahead. So my two values that you should come up with is $17.50 and $19.56. Now, the last thing, once again, we always have to write our statement at the very end. We are 90% confident the population mean for, let's see, average expense for gas is between $17.50 and $19.56. And the way gas prices are right now, that's probably pretty close to where we're at. But once again, you need to make sure you get this statement down here at the very end. Once again, we are trying to predict a population mean here. We're trying to predict a population mean. And we're 90% confident that it's going to be between these two values. That means, once again, we're 10% not confident it's going to be between those two values. But it's 90% confident I'm going to be in there. And if you're 90% confident, you feel pretty good about that. You put $100 out there and you're going to bet $100 and say, you know what, I'm 90% confident I'm going to win another $100 back. You're probably going to do that. You're probably going to do that. If you're 99% confident, yeah, I'm all in. That's 1% chance of me not doing it. That's 99% chance I am going to get it. So this is your confidence interval for a t-value. These are just additional problems. Don't worry about them. I put a worksheet on Classroom. Go ahead and work yourself through the worksheet. Tomorrow we'll talk about population or a population proportion, looking at a population proportion. But this is, once again, you're doing the exact same thing as you just did the last couple days. The only difference is now you're finding a t-value in here rather than a z-value. Okay, so go ahead and work on your homework. If you have any questions, feel free to ask, comment any questions. I'll get back to you as quickly as possible. Other than that, stay safe, keep your social distancing out there. Adios. Miss you guys. Have a good day.